Hi everyone, and welcome to this video lecture in which I will explain to you a phenomenon called resonance. This is a special case of a single degree of freedom system externally excited by a force F that is harmonic. So you can see here on the right hand side that this is an harmonic function. And how to solve this in general, I have already explained in the previous lecture. And there we encountered the situation that if we have no damping, so if the system is undamped and the excitation frequency equals the natural frequency, we find a very strange situation that the response, that the solution we obtain is something like infinity cosine omega t. Now this is of course very strange, and in fact this solution is incorrect. And in this lecture I'm going to explain to you why it is incorrect and also what is the appropriate solution. So let me first explain to you why this solution does not work. Well, if you think about the solution as the sum of the homogeneous solution and particular solution, like this, and the homogeneous solution is easy. That was just C1 cosine omega nt plus C2 times the sine of omega nt. All right. Then let's now see what this particular solution must be. Well, let's have a look at the equation of motion for this specific case. We have it like this, without damping, right hand side, where omega is omega n. Okay, so using the method of undetermined coefficients, we would normally try a cosine of omega nt, or maybe a cosine sine combination omega nt. But look, this is already in the homogeneous solution. So what we would normally try for xp is already in xh. So that means if we try this particular solution, substitute it in the equation of motion, the result will be 0 and not f cosine omega nt. So clearly this does not work for the case that zeta is 0 and omega is omega n. So in order to fix this, we need to look back at the theory of ODEs to find a method that will work in this case. And this is the so-called variations of constants. Variation of constants to find xp. All right. Maybe you remember variations of constants by heart, or maybe you remember the result, how to modify xp. If not, I made a lecture on this. Have a look at it again, and then the result, and that is what I will need here. The result is that we try for xp as a function of time what we would have tried otherwise, but now multiplied by a factor of t. So we are going to try with solving this equation like this, omega n t. Okay, I also need the expression for the velocity and the acceleration. Let's do the velocity first. Differentiation requires the product rule here. So we have a1 times the cosine of omega n t, but also produced is minus omega n times a1 times t times the sine of omega nt. And also for the second term, we produce a2 times the sine of omega nt, and we have also omega n times a2 times t times the cosine of omega nt. Okay, now for the acceleration we differentiate once more. So the derivative of the cosine, that will give me the minus sine with omega n in front. But let's have a look at this second term. If we differentiate with respect to this t, then we produce again the same term. So we have minus 2 omega n a1 times the sine of omega nt. And this second term also gives us minus omega n squared times a1 times the times t times the cosine of omega nt. Now, similarly for these two remaining terms, we get 2 omega n a2 times the cosine of omega nt. And then we have the cosine differentiated becomes a sine. So we have minus omega n squared a2 times t times the sine of omega nt. So quite a lengthy expression. What we need to do now is substitute this into the equation of motion right here. You can see that that becomes quite lengthy, but before we start really writing it down, let's focus on all the terms that contain a t. So here we have a t cosine term, minus omega n squared a1t. And here we have a1t times the cosine, which upon substitution will cancel. That maybe I should have done that first, because this equation of motion can be rewritten to standard form, x double dot plus omega n squared x is equal to f divided by k omega n squared cosine omega nt. If we substitute it in this, you can immediately see that it is being cancelled. And the same holds for this term with this t here and the sine. That will be cancelled against this term, which upon substitution in this normalized equation of motion will be multiplied by omega n squared. So that is good. So in fact, the only thing that remains on the left hand side are these two terms in the acceleration. So we get a minus 2 omega n a1 sine omega nt plus 2 omega n a2 times the cosine of omega nt. And this should be equal to f divided by k omega n squared times the cosine of omega nt. All right. I have two unknown coefficients, a1 and a2, and I can determine them by equating left and right the cosines and sine terms. So if I compare the sine terms, we just have that minus 2 omega n times a1 should be equal to 0, because there are no sine terms on the right hand side. So this means that a1 is equal to 0. Apparently, there are no cosines in the response. And similarly, we have 2 omega n times a2, which should be equal to f divided by k times omega n squared. And from this we can solve for a2, which is then f divided by 2k times omega n without the square. So what we saw is that we tried this particular solution that is being multiplied by a factor of t, and indeed upon substitution we see that it works. We can find a1 and a2 for which it is a good solution, hence it is a good try. So that means that the particular solution as a function of time will be f divided by 2k times omega n t times the sine of omega nt. So from this we can now, this is now the mathematical solution of the differential equation, but you can see that we have for this part vibration. So the excitation is in the natural frequency, the response will also be in the natural frequency. But what we can see from this amplitude is that this amplitude increases increases in time. So what we determined in last lecture, I discussed about the steady state solution, and we saw that in steady state apparently we find for this specific case infinite. Very strange. Now this is the correct solution, and what we can see here is that the solution keeps on increasing in amplitude in time. So in fact there is no such thing as a steady state here. With every additional oscillation, energy is being put into the system. The amplitude keeps on increasing and increasing. So this is what we will call resonance. And it happens, and that is important. The conditions for resonance is that we have no damping and that the natural frequency equals the excitation frequency. Then of course in practical circumstances we are close to resonance when we have a little bit of damping and when the excitation frequency is close to the natural frequency. So formally then we need to refer back to the solution I derived in the previous lecture, but you might understand from this scenario that in these cases the vibration amplitudes will also be very, very large. Alright, very well. This was the last lecture on single degree of freedom systems. I think with this you have a very good overview of all the problems you can encounter on systems with 1 degree of freedom. Thanks so much for watching. I'll see you next time.